thank you everyone for joining our webinar today, hosted by Heraflux Technologies and Sanity Solutions. Like David was saying, we certainly appreciate you taking time out of your busy schedules just to learn some tips and tricks for virtualizing SQL workloads. Be sure to stick around until the end of the webinar, where we'll be providing details on those lucky participants who qualified for the special one-on-one session with our SQL expert, David Klee. A couple of housekeeping items before we get started. First off, we do ask that everyone please mute their microphone so that there's no unwanted background noise. We will have some folks monitoring that aspect, and you will potentially get muted if any noise does come across. If there are any questions during this presentation, again, we want this to be helpful for everyone. So if there's questions, we encourage you to use the Q&A feature in the webinar platform up at the top. We will have time at the end of this session to address any of those questions. And like David said, we'll run over if possible to make sure that everyone gets the answers that they need. With that, let me introduce today's main speaker, David Klee.
Hi, everybody. So my name is David Klee. I am the founder and chief architect of Heraflux Technologies. You'll also see founder of Sequilibrium Education on there. Contact info is up on the screen. I am lucky enough to be both a Microsoft Data Platform MVP and a VMware vExpert. Basically means I spend a lot of time playing with a lot of really big toys every single day. We have a lot of fun with this stuff. I've been living SQL Server since 1996. I've been virtualizing SQL Server in production environments since 2004. And about 9 years ago, I started Heraflux Technologies, where we focus in on how Microsoft SQL Server just absolutely abuses all the infrastructure around and underneath it. So public cloud, private cloud, VMware, Hyper-V, we deal with Windows and SQL Server on Linux and have a really heavy emphasis on compute storage, enterprise all-flash storage, and really just making sure that everything is highly performant, it's highly available, and that this thing just works.
And my name is Craig Casey. I'm a senior solutions architect with Sanity Solutions. I am based in our Utah territory. Prior to joining Sanity, I had a variety of roles throughout the Salt Lake area, which included system administration and IT management. So sat in a lot of your shoes from a day-to-day perspective, understand the challenges you face. I've been woken up at 3 a.m. because an AC unit went out in the data center. So I've had those midnight wake-up calls. For those of you not familiar with Sanity Solutions, we are a solutions provider headquartered in the Denver area with local account teams in Minnesota, Utah, and Colorado. We were founded in 2004 with an emphasis on storage. Over the years, we've grown to encompass not only all data center infrastructure, which includes networking and hyper-converged infrastructure, but also advising our customers on cloud best practices and ways to move to the cloud. We've also looked at the industry and understand the importance cybersecurity can play in day-to-day IT infrastructure. Because of that, we've built out our cybersecurity practice and have specialists that focus on that vertical. Lastly, today's topic falls under a branch of Sanity Solutions called Sanity RX, which is our professional services brand. Our services range to include not only traditional deployments of infrastructure, but also assessments, which we dub sanity checks. Along with migration assistance, whether that's to or from cloud, Office 365, along with a co-managed offering for your routine upkeep of your equipment, which we call Sanity as a Service. I encourage everyone, if you're not familiar with Sanity RX, to reach out to your respective account teams or to the Heraflux group to learn more about us.
Come on, there we go. Gotta love presentations. Okay. What we're going to talk about today is one piece of a much larger puzzle in your environment. So when you look at modern data centers, cloud, on-prem, doesn't matter. It's all the same stuff, just with automation on top. We're looking at how Microsoft SQL Server just doesn't play well with others. Now, it's one piece of the puzzle here. You've got applications, you've got virtualization, you got physical compute, networking, storage, all kinds of good stuff. SQL Server is one of those big pieces that everybody's got to deal with, but is it running the best that it can? Are you getting the most for how much you're actually spending on this stuff? It's always interesting. When we look at SQL Server, most of the time it's just a four-letter word for a lot of us. But realistically, it's the keys to the kingdom. It contains all the data that the business needs in order to function. So a lot of times this really is the core of a business critical application. Now, when we look at how this thing is actually running, it's 2022. Virtualization is the assumption, but not all of these servers are virtualized yet. A lot of folks, unfortunately, treat these as just another workload in the environment. It's not always the case. These are unique snowflakes. They have some very unique needs, and a lot of times these things can just crush your environment. It is one piece of the bigger picture, but it's arguably a foundational piece. These are business critical systems, and if you look at the infrastructure stack on the right there, it fits in quite nicely around everything else. But if this isn't running, the business usually shuts down.
Like David said, SQL's not just another workload or not just another VM. It will use up all of the resources you provided, both physical and virtual, and it's always going to ask for more. It's always going to look like it needs more resources. I like to compare SQL to Pac-Man. So it's going around, it's gobbling up all the little pellets that it can, and it's always hungry for more. Because of that, you have to be cognizant of the surrounding infrastructure and VMs as well, because it will impact their performance unless you take steps to mitigate that.
Exactly. Yeah, SQL Server, it beats up on storage, it beats up on CPU, it eats all the RAM around it, just like you said. So I've been virtualizing SQL Server professionally in production environments since 2004. And now I feel like one of those old curmudgeons in IT. But realistically, there are 5 top items that, quite frankly, are poorly documented, that are just overlooked and omitted and missed in so many of these enterprise environments that we see. So we're going to talk through these today and figure out what to do about them. So item number 1, it's not having a baseline. If somebody says it's slow, what's it doing when it's running fine? We don't know. We don't know where things are at steady state. And then virtual CPU presentation. And this is assigning the virtual CPUs and making sure that the database aligns with the virtual machine and the physical machine. Then there's right sizing, and this goes into licensing, it goes into performance, goes into all kinds of stuff. And then the hypervisor storage queuing itself, and cloud and on-prem, it all matters. And then once we can deal with cleaning that up, then it's assigning the virtual disks to the virtual machine and making sure the SQL Server workload lines up properly with the way the disks have been presented and actually mapped to everything underneath. So let's start with baselines. So step number 1, do you have a baseline? If everybody is saying it's slow, how do you know what a normal Thursday afternoon is actually doing? Most of the time, we don't have this. We use a baseline to identify the consumption rates on all the stuff assigned to it. It's basically an indicator. It's like a speedometer in a car. It's an indication of what you're asking this thing to do and how it's delivering that. So really, what are we actually using in your environment? A lot of times, DBAs, and I'll be very, very nice, DBAs don't have the most deep background on hardware and infrastructure technologies. So they either go by what the third-party vendor says you need or by what they think you need. And in a lot of cases, you are just throwing oodles of hardware at this stuff, be it physical or virtual, and you're not actually using it. On the screen here is a prime example of this. 64 core physical SQL Server. How many cores do they actually need? 4. We don't need all that stuff. So it's really a measurement. What are we asking of it? And what is the underlying platform responding? How is it handling the demand that you're placing on it? And it goes back to answering the whole, when it's slow, Is it one thing? Is it everything? Is it one module? Is it during business hours? Is it only in the middle of the night when backups run? We don't know until we understand what it's doing on a daily basis. Now, you may have some third-party tools that do this, but watch the granularity in there. A lot of times you may say, hey, you look at the chart here. Well, if I look at yesterday, we got a 40% CPU spike, so we need all these cores. Well, it's in the middle of the night in a non-time sensitive environment, and that changes your baseline. It changes what you actually need. So when we look at the problem here, we don't just mean that it's hardware that you've thrown at a performance problem. If you look at on-prem, this is VMware. Hey, look, 16 CPUs, 32 gigs of RAM. Look at the cloud, 8 CPUs, 32 gigs of RAM, same number of disks. Guess what? It's the same thing. It's just a different layer. We may not have access to some of this stuff. How do we know what these things are actually doing? So if you don't have the budget for a fancy third-party tool that tries to give you a baseline, but usually don't very well, you do actually have something that's already in your toolbox. You have Windows PowerShell. You have Windows Perfmon. Guess what? We've got a PowerShell script out there that allows you to collect Windows Perfmon data on your machines. Hit a script, let it run nightly. You can automate this stuff, and it loads it into a database. So now any of the reporting tools that you may be familiar with, like Power BI, Tableau, T-SQL, Excel, whatever, you can get this. It's in a raw format. You can go load this up. Contact us. We actually have a document that shows you how to set up Windows Perfmon the way we like to see it, and it goes a long way to helping you understand what the stuff is actually doing. Now, item number 2. Virtual CPU presentation. And this one can get really deep. Quite frankly, we run a boot camp on this. This is a 9-hour topic right here, and I'm boiling it down to about 10 minutes. So I'm going to fly through this. Bottom line, don't do this. This is incorrect vCPU presentation. By the way, all electronics are powered by smoke, because when you let the smoke out, it doesn't work anymore. So, cause and correlation, all electronics are powered by smoke. Realistically, virtual CPU presentation are arguably the most important component of your SQL Server virtual machine config. The reason is because your SQL Server licensing is driven off of this core count. So if we assign too many cores, we have to pay for that many cores, and this stuff is not cheap. A lot of these SQL Server licensing figures quite literally mean the environment underneath is a rounding error on your budget line item list. So let's start with some basics. When we say CPU, what we're actually talking about could be one of different things. The actual chip that you see on that main board is called a CPU package. So it's not just core speed that we care about. There's multiple CPU processing cores in here. There's L1 and L2 cache. There's some really fast memory that's shared between them called last level cache or L3 cache. And then there's this fancy thing because of marketing called the uncore. The thing that I want you to worry about there is it has a memory controller in there. This is important for a few minutes from now. Now, that's a CPU package. So if you look at this, fancy image of somebody standing around some old conduit, it's kind of weird. That's a main board. We have a CPU package socket 1 and 2. So essentially, this thing holds 2 CPU packages on here. Now, the black and blue slots next to it, that's memory. Why is it all split apart like this? Why don't we just have one? Well, it's all about trying to make the most efficient use of the little amount of space that we have on this thing. So there's this concept called NUMA, or non-uniform memory access architecture. And what we've got, on that main board, we've got 2 CPU packages. Each one has cores, each one has its own memory controller. Right next to this thing, we've got memory. Now, CPU package 0 can access the memory connected to CPU package 1, but it doesn't have the direct ability to do so. It goes CPU package 0, and then it hops through these interconnects to package 1, and then accesses your RAM, and then goes back. Now, if you kind of look at this, what we need to do is minimize the hops between these CPUs in order to keep things quick. So now, here's another image of a main board, 2 CPU sockets, bunch of memory. That highlighted in red here is a NUMA node. It's a socket and all the memory associated with it. Now, some of the most modern chips even have something called sub-cluster NUMA, cluster on die. The AMD EPYC chips will actually have 2 of these things on one CPU package. These are important because we need to make sure that our SQL Server workload knows how to align with this stuff, not just will it, but we got to set the foundation so that it can. So virtual machine NUMA is an extension of this. When you build a virtual machine, you have the ability to define the number of sockets and the number of cores that are assigned to that virtual machine. And what we need to do is understand our physical CPU topology to make sure that this workload best matches or tries to fit tightly inside all this stuff underneath. We have to do this to maintain performance on there. So first of all, understand the right-sized amount of CPUs that you need on your workload. And we'll talk a little bit more about that in a minute. But now let's just say that we have done all the homework. We know how many cores this workload actually needs. If the workload, core count, and memory count fit inside one of the physical socket NUMA nodes on your environment, build the VM as such. So let's say we got a 10-core SQL Server VM with 64 gigs of RAM. Pretty normal. Well, 10 fits inside 12 pretty comfortably. 64 gigs of RAM fits inside the 256 gig on that socket. Build it for one socket by 10 cores. No problem. It's really, really easy. If the workload is bigger than one of these sockets, cut it in half. Build a 2-socket by 8-core virtual machine if we know we need all 16 cores. Same thing with the memory. Do this, and the virtual machine will then map itself to these individual sockets underneath, and this awareness of what the physical topology actually looks like gets presented through the physical machine, through the virtual machine, into the operating system where your application workloads can pick up on this. And that's really, really important. This is one of those areas that people get wrong all the time. And it's not because anybody's doing anything wrong, but because it's so easy and it's not flagged to get this stuff incorrect. You can verify this pretty comfortably. Now, if you are working with SQL Server directly, right-click on the instance, hit Properties, go to Processor, and there you see our NUMA nodes as Windows sees it. Now, if you want to get a little more nerdy, there's a thing called a SQL Server Dynamic Management View. We can do select stuff from sys.dmos nodes. And there you go. We have 4 NUMA nodes on here, each with 3 CPUs and 3 online schedulers. That tells me this thing is lined up right. The things we got to watch out for. Nodes listed as offline. Other times, there's different numbers of online schedulers compared to the CPUs on there. And there are some really easy ways that this can happen. I'm not exaggerating this. I caught this at a major environment just last week. It's big. So here's where these things get into trouble. Windows and SQL Server Standard Edition have NUMA limitations on here. And if you misalign the virtual machine, you can cause cores to go unused. You can cause other problems with this. So let's just say, literally, you picked a 24-core VM and hit go. By default, it's going to build you a 12-socket by 2-core virtual machine. Guess what? SQL Standard Edition and Windows Standard Edition are able to address all 24 cores or 4 sockets worth of cores, whichever are lower. Boom! You just realized that you can't use 2/3 of the CPUs that you assigned on here. And guess what? Windows does the same thing. And I have seen this or worse scenario where Windows and SQL Server couldn't agree on which cores they couldn't use. So they were duking it out under the hood. No exaggeration. A 9-to-5 shop had a 24-core SQL Server running 90% busy around the clock. We went in and cleaned this up. When we were done, it dropped to 10% busy, and we're actually able to go all the way down to a 4-core SQL Server and save all that licensing. That's a big deal. Now, how many cores do we actually need? There's a technical reason why the act of throwing hardware at this stuff is not always the right solution. So let me give you a little bit of background on this. Cloud is nothing more than virtualization in somebody else's data center with some really, really good automation on top of it. So everything that we're talking about here applies to on-prem and cloud technologies. If you spin up a query for a big old report and you say go, you think it just runs because it looks like it just runs, right? Well, because of the presence of the hypervisor, it's not always the case. When you hit go, there's a little bit of amount of headroom to get that command onto the hypervisor resource scheduling queue. It's tiny, but it's there. And then it may just sit there for a little while. There's time spent in this, I'm ready to run, but it's not ready yet, queue. VMware and a lot of the other hypervisor call it %ready time. It means it's ready to go, but we're not ready yet for it. And then it starts running. But it doesn't mean that it can't get paused, because guess what? This queue is not necessarily first in, first out. It can be interrupted. We can go from a running state to a waiting state for anything else. We can go into a CPU ready state, which means we're waiting for these other CPUs to get through the queues. We could go into a co-stop state, which means, hey, one of the CPUs is a lot further ahead in the queues than the others, so we got to pause that to let the other guys catch up. And it can do this and go in and out of the state all over the place. And during this entire time, we may have efficiency losses, and it could be CPU power savings are turned on the physical machine, or we're trying to put this process on a hyper-threaded core and the physical core behind it might be really busy. It could be all kinds of stuff. Now, I know this sounds severe. In the right configured environment, this entire active overhead right here, less than 1/4% in total penalty. And that's at worst. Most of the time we can get this to less than 1/20th of 1%. And that's amazing. That's how good modern CPUs and modern hypervisors really are. But if you get this wrong, it's not good. So what we need to do, how many CPUs does this SQL Server actually need? Right size. Allocate what you need for today with a reasonable amount of headroom, of course. But if you need 8 cores, don't give it 64, give it 10. Give it a little bit extra headroom in there. We need to reduce the number of objects in the scheduler. And because we're juggling less of these things, we can reduce the amount of time stuck in the scheduler. So we make it faster, and because we're cutting down the allocated resources, we can save you money. It gets really interesting. So, I mean, the prime example of that, just literally, this guy on the left, these are real numbers from real client environments. You don't need 64 cores on this thing. They thought they did. We got it down to 8, and realistically, we could have gone down to 4. And then with a little bit of tuning at the database layer, we could probably get it to 2, believe it or not. Now, the reason this stuff the reason it adds up so much is that the SQL Server licensing costs so much. It's not as bad as some other DBMSs out there, but it adds up. So if we're looking at the modern version of SQL Server 2019, there's developer editions, pre-production, it's free. There's web edition, it's only really used for hosting companies under the SPLA license agreements. You're limited on resources. Most people don't use this. Most of the time, they're on standard or enterprise. Enterprise is the flagship. We can license by physical machine. We can license by core. You get everything. Standard edition has got some resource limits on there. You have less flexibility with virtual machines most of the time. It all depends on how you buy this stuff. So you can buy it by VM. This is standard edition or enterprise edition. You have a minimum of 4 virtual CPU cores that you have to buy and then increase by 2. Now, MSRP on this without software assurance, and you do need software assurance, MSRP is about $3,700 for 2 cores. So do the math on that. You can do this by host without software assurance, only with Enterprise Edition only, and that's about $13,500 for 4 or for 2 cores. So again, it adds up. There's a lot of limitations if you don't buy software assurance. If you do buy software assurance, it adds up. But over time, it's actually cheaper if you're going to maintain this stuff. And essentially, you license all the physical cores in the physical machine, buy SA for all of it, and then you can pack as many SQL Server VMs on there as you can possibly fit while maintaining performance. That's what I recommend for larger environments. Now, networking. Actually, we're not really going to talk about networking. Just please make sure that your data centers don't look like this.
And if your data centers do look like that, feel free to give us a call. And we have a networking overlay team that can come in and clean that up for you.
Exactly. Call them, not us, for this, because my first instinct is to walk in here with a pair of hedge clippers and just go to town. What we're actually going to talk about, item number 4, is storage queuing. Now, this is one of the biggest areas, and we're going to spend a little more time on this than some of the others here. When it comes to enterprise storage, historically, what we end up with is a state to where all the SAN vendors, like throughput, IOPS, you need more IOPS, you need more IOPS, you need 2 million IOPS. No, speed matters. I need it to be faster based on the demand. I need to be faster than the demand we're asking of it. But what really matters is the speed at which we can get a transaction, a business data change to disk and back. It's latency. It is arguably the most important thing for any database engine, be it NoSQL, be it relational, cloud, on-prem, whatever. Now, lesser storage, we're measuring this in milliseconds. Good storage, we're measuring this in microseconds. It matters. Now, I'm not discounting IOPS or IO operations per second. Higher is always better. But I mean, think about it. If we've got a vehicle that has a speedometer at 240 miles an hour and all we're doing is going and getting groceries on it, it's a waste. Higher is better. I need the peaks of this thing to be higher than what we're asking of it. But what I really care about, 0 to 60, that's latency. Now, there's throughput, and what throughput is basically, it's IOPS times block size of the request, just really usually measured in megabytes per second. So all you got to do here, monitor to make sure that your interconnects are not getting saturated. Monitor to make sure that with the load testing you've done when you first turn that storage array on, and you did do the load testing on there, right? Make sure that the demand is not exceeding what this thing is capable of, and then really hone in on the latency. This matters so much more than everybody realizes. Now, there are really challenging states with this. If you look at an on-prem data center, and cloud always applies here, these are the challenges we see. And no exaggeration, these are real numbers. We get pulled in all the time when there's discrepancies between what the database administrators are actually seeing and what everybody else is seeing in the environment. There's a measurement that DBAs are looking at called disk stall. It's essentially storage latency. It's just called a little bit different, but it's within the database engine itself. And a lot of times we're going to see elevated disk read and write stalls. These are the things that wake DBAs up in the middle of the night. And unfortunately, you as infrastructure admins, these are the things they're going to wake you up for. And then you wake up, you turn on your computer, you remote in, you take a good look at the storage, you're like 0.6 write latency. You're smoking crack, go back to bed. Your telemetry is lying to you. Unfortunately, both of you are right, but nobody ever sees it like that. It's always, I'm right, you're wrong, because this is what my telemetry is showing me. The problem is, these are both valid points of view from its perspective, because there are a whole lot of queues in between those two layers. In fact, there are so many of them. When we really map out the enterprise environment here, at the bottom, enterprise storage. So now, the individual storage medium itself can be a bottleneck. There's cache memory. There's processors on the controller. There's interconnects on the controller. There's saturation of individual ports on either networking or fiber interconnects between everything. There may be CPU contention on there. There may be misconfigurations on there that don't let you go fast enough. Then you've got the interconnects to get into the back of the physical machine. There can be queue depth settings there that are a problem. You could saturate those. You may not have enough interconnects. Then you hit the physical machine. You may be bottlenecked on CPU and memory, all related to storage traffic handling. Now hit the virtual machine configuration itself. There's storage controllers that handle queuing related to the disks themselves. And there's queues in Windows and Linux for the individual drive. And there's a storage engine inside SQL Server. And there's a database that's got its own level of storage contention in there. And the database is made up of one or more data files in a log file. There could be contention in there. So realistically, that's an individual machine. Now scale this out. What if you've got 10 SQL servers? What if you have 100 SQL servers? We have one environment, they have 180,000 SQL servers. Yeah, tune that. It's a lot of fun. And it all starts at these foundational level components. So we're just going to hit some of the big ones on here. If you are running fiber, guess what? There is a queue depth setting in your fiber HBA. And this can also be FCOE adapters for all of your converged environments. Prime example of this, and I see this everywhere. Cisco UCS has a default LUN queue depth of 20. It is buried in the FC adapter policy for whatever platform you're running. But guess what? It's kind of like connecting a fire hose to a straw. Modern flash storage can handle a queue depth of easily 128, maybe 256, maybe even more. This value of 20 is like putting square tires on a Ferrari. It's not fun. Now, if you're not on Cisco UCS, it still applies. Other adapters, like Mellanox, Broadcom, QLogic, Emulex, all these, they have default queue depths of either 32 or 64. They do this because they don't know what kind of storage you're going to connect to this, and it's their design to protect the storage. They want it low so that you're not pushing and breaking the array. If you're on good storage, it's far too low. Literally, it's a Ferrari with square tires and 1 gallon gas tank. You're not going fast at all. Review these settings. We have to start at the very bottom. So if you're doing tuning here, before you tune anything else above this, you have to go clean this setting up. Now, if you were on VMware, that setting that you changed there, you need to tell VMware what this queue depth setting change actually is. So there's a VMware KB article that tells you how to do it. But if you change the Cisco UCS SCOE adapter queue depth, or an Emulex or QLogic queue depth, there's an equivalent setting in VMware to go change. It's very straightforward. It's pretty easy to go audit and make sure everything looks okay, but you do need to do that. There's a guide here from Cisco UCS that shows you how to do this. The VMware KB article lists a lot of details around some of these other vendors on there. Please go double check this. It really does matter. Now, if you're not fiber, if you are running iSCSI, believe it or not, this is actually one of the reasons why iSCSI outperforms fiber by default, because the default queue depth here is 128. Well, in most environments, that might actually be acceptable. But if you're on a really good all-flash array or an NVMe array, consider bumping this value up. Now, check with your storage vendor to make sure that everything is okay. But a lot of times we can bump this up to 192, 256, and we can end up with more concurrent I/O making it to the SAN, and it can handle it. And therefore, we get better performance, we get lower latency, and everything is good. So same kind of thing. The document on the screen here shows you how to go update this for VMware. It lists 6.5, but it works all the way up to 7.0 and whatever's coming. Now, this is something that works not just for VMware, but for Hyper-V. And if you're doing in-guest iSCSI with cloud SAN storage or other storage vendors that tell you to do in-guest stuff, this matters as well. It's just the Windows side. Now, this one I'm going to be a little more long-winded on. This one is VMware specific, and it gets really, really interesting. Fix that. There we go. Okay. VMware, in their infinite wisdom, calls a virtual machine and its dependent virtual disks a world. If one world, and only one world, exists on a SAN LUN formatted as a VMware data store, the queue depth to that LUN at that host is inherited from the virtual machine. We'll talk about that layer here in a minute. The problem here is that if more than one world exists on that data store, and almost always this is the case, the queue depth at that host to that data store is arbitrarily dropped to 32. And if you've got SIOC enabled, it can actually decrease it even lower. And that is a problem. It's a setting called disk.sched_num_rec_outstanding, or DSNRO for short. Say that 3 times fast. It's one of those things. This is why when people were seeing performance gains with RDMs or vVols, you're working around this setting that nobody knows about. So what you got to go do, you can go adjust this per host, per LUN, and you don't even have to do it to all. You can do it to the ones that you need it. Go adjust this. If you're on good storage, all flash or flash storage, you definitely want to go bump this up. On most all-flash storage arrays, we're comfortable bumping this all the way up to 128. Do the appropriate testing, of course. Some storage arrays that are just really, really fast will go even higher. It really does make a big difference. But this is arguably one of the silent performance killers to when you look at the telemetry coming out of the SAN. You say, SAN LUN here looks great. And then you look at Windows and everything's just off the charts bad. This is probably why. So fix this. We can help you with that. Now, if you're NFS, like NetApp arrays, check with the vendor, but there are some other tuning components that you can do there. There's max volume, heap size, all kinds of good stuff. There's a VMNIC ring size. There's a VMware article here that talks through how to do this. If you're NFS 3, a lot of times it doesn't round robin. It won't use more than one connection for a given command. So you might want to think about LACP for port aggregation and not just for port redundancy. If you're NFS 4.1, that will do round robining in there, so you may get some better multipathing in there. So double check all of that. Whew. Okay. Virtual disk presentation. So we've cleaned up the physical side of storage. Let's move into the VM. So literally same exact screenshot here. They're virtual disks in Azure and in VMware and Hyper-V and Nutanix and all these other guys. It's the same thing. It's virtual files on a virtual file system connected to a virtual machine that acts and looks, passes a sniff test. It's just storage connected to a VM. But you got to connect it somehow. So on-prem, with any of the hypervisors out there, you can't just connect a drive to a VM. You have to have a storage controller to connect it to. Same thing with physical servers. You can't just, drop a hard drive on a main board and expect it to work. You have to have a connection mechanism of some kind. So in VMware and Hyper-V and Nutanix, you get 4 controllers max of type SCSI. It's a legacy emulation, but it works just fine. The hypervisor and the virtual machine do disk command coalescing, not just by the disks, but by the controllers. Each one of these controllers have an associated queue depth. It's something not a lot of folks know, but this is where we can get a speed gain. We do have different types of controllers. So on VMware, you get LSI Logic Parallel, LSI Logic SAS, VMware Paravirtual SCSI, and NVMe. If you're on Hyper-V, it just says controller. What it really is the LSI Logic SAS controller. It's built into the operating system. The driver's there. Everything's fine. The LSI Logic SAS controller for VMware and Hyper-V has a default non-changeable queue depth of just 32 concurrent storage operations. So think of the queue depths underneath. If we don't touch a Cisco UCS environment and we have one controller here and we don't touch DSNRO, you can push 32 concurrent storage commands here and the UCS blade profile is capped at 20, instant bottleneck. Clean that up. Go up to 128, okay? DSNRO. 32, 32, still can stack up, especially if you have more than one controller. If you do 4 controllers, the Paravirtual SCSI controller has a queue depth maximum of 64, and with a registry setting, you can go to 254. The NVMe controller, you have multiple queues per controller. Each queue has a queue depth of like 65,000, but there's some trade-offs with that one. You can't expand a drive after you've attached it unless you reboot the machine. Kind of annoying. What we really care about here is we want to leverage all available controllers. And in this case, if you're on VMware, we definitely want you to use a Paravirtual SCSI controller. If you're on Hyper-V, use all 4 controllers. Here's how you do this. You assign the controllers to the virtual machine, make sure the type is set right, and then shut the VM down. Edit the virtual machine hard drive. There's a thing called a virtual device node, and in Hyper-V, it's buried in there. You just pick the controller in the slot. In VMware, they call it the virtual device node. You pick the controller, and then you get up to, I believe, 30 slots per controller. And what you can do is figure out how to go balance this stuff. Now, how do you balance it? This is where things get interesting. DBAs have this habit, and it's a good habit, of spreading data around to multiple drives. This is one of the things that they did a long time ago, because guess what? There were queues back then too. So spreading the workload out for different types of workloads and different pieces of the puzzle, you get better performance. Same exact thing applies here. We just put a V in front of everything and call it good. So if this is a SQL Server virtual machine, we're going to assume we have 4 Paravirtual SCSI controllers. Common practice, split out the operating system, split out where the SQL Server is installed, split out where the system databases are loaded at. And now we'll have one or more than one drive for our database of data. We'll have one or more than one for our SQL Server transaction logs. It's kind of a ledger that records everything that changes in that database. We've got the TempDB database, kind of this garbage can dumping ground of all kinds of stuff in the SQL Server, but it is pretty active. So generally speaking, we want that off on its own drive. And then if you're doing local backups, we need that as well. So how do you balance this stuff? You only get 4 controllers. I wish we had more. What you have to do is use whatever system telemetry, and if you don't have any, get Perfmon set up and running, because then you can figure out how to go balance this workload out there. Standardize the best you can, but these are unique snowflakes. Sometimes we can get really complex on here. An individual database can have hundreds of database files on disk because there's a lot of logical separation that DBAs can do. You may have different file groups that have, people data and then sales data, and all you can split it up 1,000 different ways. You may end up with a lot of different drives, a lot of different files on drives. Use the telemetry that you've got to look at the workloads and look for complementary workloads instead of colliding workloads to get rid of hotspots on these queues. You can do this. Now, a lot of times, DBAs aren't aware of how to do this. So there's a blog post that will pop up here in a second that shows you how do you add more drives and more data files into a database and spread this data around. So if you're interested, send this to your DBAs. There's a blog post here on my home blog. How do we actually scale out this workload and move the data and balance it so that the database engine will round robin between them? We go to more queues, we go to more drives, we get better parallelism of storage activity all the way through the entire stack. That's kind of the last vestige of tuning this stuff, and a lot of people stop before they hit this point, and then you end up with a bottleneck inside the database engine that Windows isn't even seeing, and the DBAs still complain, like rightfully so, because their layer of telemetry is showing them that layer of info that says everything's bad. Now, none of this doesn't apply to the cloud. It's literally just hypervisors out there. So how do we deal with cloud storage? Now, we don't have direct access to a lot of this stuff, but you do have access to the virtual disks themselves. There are limitations on here. They do this to keep their resources in check and arguably to have you pay more. So let's just say I pick a 1 terabyte virtual drive out there, P30 on Microsoft Azure. You get 5,000 provision IOPS, 200 megabytes per second of throughput. Is this good? Is it bad? I don't know. What are you using? What are you demanding of that workload? And that all goes back to that baseline. There's burstable IOPS for some of these virtual machine disk scales. There's throughput ceilings on here. There's read and write caching, and read caching is okay. Sometimes we don't want to do write caching underneath SQL Server. It's all based on arguably the performance tier of disks and how big of disk you provision. Unless you know what your workload is demanding of the underlying storage today, you can't size this stuff properly for speed. You can just price it based on space consumed. And if I have a 128 gig database, we're maxed out at 500 IOPS and 100 megabytes per second. The second I start running some of these big old reports that a lot of people throw at this, immediate performance cap. So now, look at the virtual machine tiers. We have ultra disks, we have premium SSDs, standard SSDs, and then standard hard drives that I like to call spinning rust. The latency characteristics get better as you move to the left, but they still have performance ceilings on each of these drives. So you can do things like in-guest storage spaces. You can try to combine disks in different RAID groups, but realistically, if you work past this to get better speed, you're probably going to hit the performance cap at the virtual machine scale. Yay! I like ceilings and artificial caps. Not the most fun. So if we take a look at this, every virtual machine scale, regardless of the virtual disks that you connect, have throughput and IOPS caps as well. You have to be cognizant of this, and it all goes back to the baselines. What are you actually consuming today? And after you move to the cloud, are you encountering any of these things? What you'll see in guest is that they throttle the storage speed, so your latency in guest just skyrockets and everything slows down. It's not the most fun. So be aware of this. This is cumulative for all the virtual disks and all the demand on this machine. There are also some alternatives on the cloud that we may or may not be aware of. If you're on Azure, there's Azure NetApp Files. It's essentially SMB or NFS connections for your individual workloads. It does work really well. There's also Cloud iSCSI SANs, and these work great. The virtual machine networks do have higher performance ceilings than the virtual disks. So if your workload demands it, this might be a good alternative. So let us know. We do a lot of this kind of stuff. So that was a lot of technical details in there. The recording will be made available. Please use this as a checklist. I want this to be more foundational because these workloads, they're so advanced. There's so many pieces of the puzzle. We have to tune these in order. If you start tuning at the top, you just make it worse. So clean up the SAN itself, and then clean up the interconnects between them. Make sure you're monitoring everything and it looks fine. Clean up all the queues at the physical machine layer. So these HBAs, the CPU, the memory bottlenecks. Then clean up all the queues in the virtualization layer, both at the hypervisor host and at the virtual machine configuration. And then don't stop there, because the real power, now that we've opened up the foundation of this stuff, clean up the SQL Server layer itself. You can do this. More files, more file groups, more drives, widely distribute this stuff. And don't take my word for any of this stuff. Question everything anybody says, because you need to not be told this, but you need to do this, and you need to test it and verify and make sure that everything looks good. And I promise you, this is quite literally a formulaic approach that we have for how to tune and tailor a virtual environment to your workloads. It's capable of so much more than these silly defaults have in every component in there. It matters. So thank you all for tuning in. Let's open this up for some questions.
Yes, thank you, David. As we said at the beginning, feel free to use the Q&A feature within the webinar platform. If you're having any troubles accessing that, feel free to raise your hand and we can call on you and we can talk through your question as well.
Cool. So I guess I have a question for all of you. Actually, we got one right there. Go for it.
Go for it, Timothy.
I turned on the chat feature. It says chat is turned off for this meeting. So I tried to raise my hand earlier to say I can't put any questions in.
Go for it.
Just to let you know, if you're wondering why no one's chatting, it's because it's turned off.
Yeah, well, there's a Q&A function at the very top, and that's more built for this kind of stuff.
Oh, okay.
But it does work. Cool. So while we wait for some questions here, how many folks are just adamant that we are just staying on-prem because that's the right spot for this workload? And then conversely, how many companies have management that have come down and said, we're going to the cloud now? Actually, I should play with one of my little special effects here. Because then we could say, if management comes along and we just say, you're going to the cloud now, whether you like it or not. I'm easily amused.
David, one other question. Have you ever heard of people putting VMs together with 3 CPUs or 5 CPUs?
Mm-hmm. Yeah. Okay. Yeah, it sounds weird, but there's nothing technically that's going to prevent you or actually get in the way of that kind of stuff. From a SQL Server licensing perspective, the minimum is 4 and you go up by 2 after that. But I've definitely been known to do 3, especially if the virtual machine CPU scheduling is a little tight in an environment. I'll micromanage it to a point. If it's 8 or below, then yeah, I'll do 3, 4, 5, 6, 7, whatever we need to do with that in order to keep that resource scheduling footprint tight. Once we hit about 8, going from 8 to 10 to 12, I tend to go by 2s after that. Anybody else have any questions? Oh, come on. I know you've got questions out there.
The presentation was so good, David, that you answered all the questions.
Now, for everybody out there, if you have questions long-term, do not hesitate to reach out. Our contact info are in the slides. We'll have the recording up on YouTube pretty soon. I wanted it to be more of a checklist for everybody with the flow of the presentation. And that way you can take this, you can go back to your environments, work with your infrastructure teams, work with your DBAs, go through the layers one at a time. You can do this. You really can. But a lot of these layers by default are just not good. So take it back, take it as a checklist. Let us know if you have any tech questions with this stuff. We're here to help.
And we will be reaching out to those individuals that get that one-on-one session with David to talk through their environment. So we've captured everyone who's been able to participate, and we'll be sending an email out. Hope everyone has a great day. Thank you so much for your time. Thank you for attending, and we look forward to chatting with everyone in the future.
Sounds good. Awesome. Thank you all for attending. Everybody stay safe out there, and we look forward to talking with you all soon.
Thank you, guys.
Thank you.
Thank you.